welcome you to the session on when a researcher should use optimization approach. Optimization approach is widely used across all the fields and it has a lot of importance for transportation, healthcare, medical science, robotics, and many other domains. And the optimization approaches acts as a backbone for many technology to optimize the decision making. I am Professor Jitesh Thakkar, Dean Academics and Professor Logistics and Supply Chain Management at Gati Shakti Vishwavidyalaya. Gati Shakti Vishwavidyalaya is India's first and only university in transportation and logistics sector, funded, established by Ministry of Railways, Government of India. I am an ex-professor, IIT Kharagpur, and extensively work in the domain of optimization. I would like to introduce you to the channel. The name of the channel is Professor Dr. Jitesh J. Thakkar. Currently, this channel has two playlists, faculty and student development, logistics, supply chain and infrastructure projects. And this channel shares the intellectual content to benefit faculty, student and industry professionals. You can scan this QR code on the right hand side to explore the intellectual content which is created for the benefit of student, faculty and industry professionals. About the playlist, faculty and student development. Faculty and student development is a multifaceted agenda and it requires the grooming broadly in three dimensions. Number one is enhancing teaching effectiveness using improved pedagogical skills that may be innovative teaching methods, classroom management technique, student engagement strategies, utilize educational technology and foster critical thinking for complex problems. Number two, promote research excellence and productivity by providing training in research methodologies, data analysis, and scholarly writing. And number three, enhance experiential learning through projects, internships, and exposure to real world problems. So, the purpose of this platform is to provide 360-degree development to faculty and students in the higher education institution for enhancing their capability and quality of the overall higher education system. I would like to brief you about my university, Gati Shakti Vishwavidyalaya. It is a central university created in 2022 by the Act of Parliament. GSV is established by Ministry of Railways, Government of India, and this university has a unique mandate to contribute for the entire transportation and logistics sector, including rail, road, water, aviation, ports and shipping across all three domains, technology that is infrastructure, management that is services, and policy that is regulations. Typically, it comprises multidisciplinary teaching, executive training, skilling and research, and university follows demand-driven curriculum to meet the industry needs of the transportation sector. High-quality faculty with global exposure and leveraging state-of-the-art infrastructure of centralized training institutions of Indian Railway sets a pitch and a growth path for the university. GSV is propelling the nation towards the new era of interconnectedness and sustainable development through innovations and best practices in transportation and logistics sector. University has a vision in line with the 21st century aspirations of industry, society and nation, that is innovation-led, industry-driven university. University operates with three distinct mission statements: based in the world, futuristic education and research, effective collaboration with industry and stakeholders, and number three, imbibe and internalize professional work ethics and culture to foster lifelong learning paradigms for a developed India. University offers a vast range of academic programs for both regular students as well as for working professionals to enrich the skills and the overall ecosystem of transportation and logistics sector. So university offers programs at undergraduate and postgraduate level for regular student, which includes BTech in civil engineering with specialization in rail engineering, BTech in electronics and communication engineering with specialization in rail engineering, BTech in mechanical engineering with specialization in rail engineering, BTech in electrical engineering with specialization in rail engineering, BTech in artificial intelligence and data science with specialization in transportation and logistics, BTech in aviation engineering, MBA in logistics and supply chain management, and MBA in ports and shipping logistics jointly with Indian Maritime University. On the other hand, university offers the programs in hybrid mode for working professionals to upgrade and enhance their skills to benefit the sector. And this includes MTech in Intelligent Transport Systems, MTech in Railway Engineering, MTech in Bridge and Tunnel Engineering, MTech in Roads and Highway Engineering, MBA in Logistics and Supply Chain Management, MBA Metro Rail Management, MBA Multimodal Transportation, MBA Aviation Operations Management, and PhD in Engineering and PhD in Management with a core focus on transportation and logistics sector. Typically, this video exchanges the views on very important topic when a researcher should use optimization approach. So let us take a deep dive and try to appreciate what is optimization, why this is important, what is the broader classification, application areas, and the mathematical formulation behind. I would like to cite my contributions in the optimization, and you may like to refer our few of the research paper utilizing optimization research. One of the research paper is ambulance location under temporal variation in demand using mixed coded memetic algorithm, published in Operations Research in 2022, volume 56, page numbers 2967 to 2997 by Nadar, Jha, and myself, Thakkar, J. Another paper is titled as Robust Optimization of Sustainable Food Grade Transportation with Uncertain Supply and International Disruptions. And this paper is published in International Journal of Production Research in year 2019, volume 58, number 18, pages 5651 to 5675 by Mayar Loit M and Thakkar J. myself. The third research paper I would like to mention is Environmentally Conscious Logistics Planning Considering Wastages for Food Grade Industry using Multi-Objective Hybrid Particle Swarm Optimization. Typically, it's an evolutionary algorithm published in Transportation Research Party, Logistics and Transportation Review in year 2019, volume 127, July 2019, pages 220 to 248 by Mayar Loit M and Thakkar J, that is myself. So let us look at broadly what is optimization. So the optimization research approach is a very systematic process of finding the best solution to a problem given a set of constraints and an objective to either maximize or minimize. It is a core component of operations research and is widely used in various fields like engineering, economics, logistics, computer science, healthcare, tourism, transportation. Name the field, across all the domain, optimization is highly utilized. So if you look at the key aspects of optimization, the core components, then number one is objective function. So this is the function that needs to be either maximized or minimized. If you are looking at profit, then you would like to maximize it. If you are looking at cost, you would like to minimize it. It represents the goal of optimization problem. Why am I doing this optimization and what is my objective? So maximizing profit, minimizing cost, or maximizing efficiency could be some of the objective functions. The second important element of optimization is decision variables. These are the variables that can be adjusted to achieve the desired outcomes, and the optimization process involves finding the optimal values for these variables. So you are trying to optimize the profit, and you have the different variables specific to product mix or specific to resources. Then you would like to vary these parameters, vary these variables, decision variables, to see that you can reach to the values of your variables, leading to optimization of the problem. The third is the constraint. Any real life problem always operates within set of constraints, and I must impose this constraint to define the boundary of my optimization problem. So there are limitations or restrictions that must be satisfied. They define the feasible region. I have to figure out the feasible region within which I can carry out my optimization process, and the place something where my solution should lie. So resource limitations is one of the, so manpower, man hours, equipment hours, space constraint, physical constraint, regulatory requirements, all this poses some restrictions, limitations on defining the feasible region of my problem, and they fall under the category of constraints. If you look at the overall process, the key aspects of optimization, then number one, problem formulation. Typically, I will define the problem, identify the objective function, define the decision variable and constraints. Number two, model development. So I will create a mathematical model that represents the problem, defines the boundary of the problem, and typically this model expresses objective function and constraints in a mathematical terms. Number three, solution finding. Apply optimization techniques to find the optimal solution, and this can include algorithms, mathematical programming methods, linear optimization, nonlinear optimization. It could be heuristics, it could be evolutionary algorithms. The fourth is solution evaluation. So once I have derived the solution, I need to analyze to ensure its feasibility and whether it meets the desired criteria or not. Because many a times, if you say that vendor should supply this much quantity, which is the optimal quantity, but it may not be feasible for the vendor considering the batch size, considering the packaging size, or maybe some of the transport related constraints, and hence you should look at the feasibility of implementing the optimal solution. Implement the solution in the real world setting. So broadly, we can say that we have different types of optimization techniques. Number one is linear programming, widely used technique when my objective function and constraints are linear in nature. Number two, nonlinear programming. This is used when the objective functions or constraints are nonlinear in nature. Number three, integer programming, used when some of the decision variables must be integer. So it could be binary integer programming, it could be 0-1 integer programming. For example, you want to run your mathematical formulation, your optimization problem, to find out the optimal locations of warehouses across the country, and you may have 0 and 1 integer variable, and typically it is called 0, 1 integer variable programming model. 0 means I should not locate my warehouse in a given position, given location, and 1 means I should go for the warehouse in a given site. The fifth one is heuristics. The fourth one is dynamic programming. It is used for the problems that can be broken down into smaller sub-problems. So many times you are dealing with the complex optimization, and here it's absolutely difficult, whether from analytical point of view, solution point of view, or understanding point of view, to deal with the entire problem in one go. So here you can divide the complex optimization problem into small sub-problems, and then you will try to solve the different problems, and together you will try to derive the optimal solution. The fifth one is heuristics and meta-heuristics. So many situations which are complex, typically you are dealing with the combinatorial kind of problem, and finding the exact optimal solution is computationally extremely difficult. So many integer programming problem, you can use branch and bound method, but many times it is more feasible to look for even the problem which has multimodal function. You may end up with the local optima, and that is something where you can look for the heuristics or evolutionary algorithms approach, and you can ease out in terms of your computational difficulty. So these methods provide good but not necessarily optimal. That is the caution. And you may have suboptimal feasible solution, but it is more practical because you are not compromising with many of the considerations, as your heuristics is more capable enough to handle the complexity of the problem and computational difficulty. Otherwise, you may put certain assumptions or ignore some of the complex constraints where the quality of your solution will be compromised even if you get the optimal solution. So here it's okay to have the suboptimal solution, but it is more practical because you have not put too many assumptions and not compromised with many real life considerations. So examples can be genetic algorithm, simulated annealing, particle swarm optimization, taboo search, and there are many evolutionary algorithms you can deploy, heuristics approach you can deploy to handle the computationally difficult combinatorial problems. Typically, your NP hard problem, they fall into this category. Traveling salesperson problem, you can handle it, you can solve it using the evolutionary algorithm approach with much more ease compared to the exact optimization approach. So applications of optimization, all facets you can use the optimization, but just to cite few: logistics and supply chain management, optimizing transportation routes, warehouse locations, inventory levels. Absolutely, optimization is extensively used. Manufacturing, optimizing production schedules, resource allocations, product design, even scheduling the workforce, short-term scheduling, long-term scheduling. Optimization is widely used. Finance, optimizing investment portfolio, risk management. You are investing in the mutual fund and you may like to optimize your portfolio. Trading strategies, optimization is a highly useful and most effective approach. Engineering, optimizing the design of structures. You are going for the bridges, highways, roadways, shipping structure, everywhere. You can use even circuits and other system. Optimization can extensively help. Machine learning. Yes, machine learning is a computer-based system that learns on its own through data interpretation, identifying the patterns, but doing so, there is an optimization algorithm behind, and even optimizing model parameters to improve the performance of my machine learning algorithm or machine learning system. There are a couple of unique strands of optimization. Number one, provides optimal, or if you are using heuristic, near optimal solution and helps in making the informed best possible decision. Number two, objective and data driven based on mathematical models and data analysis. So certainly there is no ambiguity involved. Number three, improves efficiency and productivity, leads to better resource utilization and cost saving. Because you are not adopting the naive approach where you are just going for trial and error and trying to see the performance of the system or impact on the system. But here, using the mathematical model, you are obtaining the optimal solution where you can have great impact on the resource utilization and the cost saving. There are certain limitations of the optimization approach. Number one, it requires well-defined problem and accurate data. So like multi-criteria decision-making technique where you have a greater flexibility to accommodate conflicting criteria, tangible, intangible, subjective, and objective, those flexibilities are not very much available with the optimization approach. So the quality of the solution depends on the accuracy of the model and the input data. Number two, can be computationally intensive. So some optimization problems, especially complex one, typically combinatorial problem, NPR problem, require significant computational resources. And third, it cannot capture all real world complexity. The model may not fully represent all the factors that influence the problem. So maybe some government interventions, government policies, the changes taking place in the external world, or maybe the political environment. There are many factors within the organization, internal or external to the organization, microeconomics as well as macroeconomics. You may not be able to capture through your mathematical model. And this is the third limitation when using the optimization approach. So broadly, if we see, then optimization research approach is a powerful tool for finding the best optimal solution to the complex problems, and it provides a structured and systematic way to improve decision making and achieve desired outcomes across a wide range of fields. Let it be engineering, management, transportation, technology, healthcare, medical science, everywhere optimization is extensively used. Let us look at the general formulation of optimization problem. So left side, you can see the objective function. It is described that minimize or maximize a function fx, where x is a vector of decision variables, and your objective is to minimize fx, typically a cost function, and you may be interested to maximize your fx, maybe revenue, market share, or the profit, where x is x1, x2, xn represents the vectors of the decision variables. And fx is the objective function, which can be linear, it can be non-linear, it can be convex, it can be non-convex. So you have different sets of mathematical optimization approaches available as you are dealing with linear, non-linear, convex or non-convex function. Typically for linear function, you make use of linear programming. As a subset of linear programming, you make use of integer programming, branch and bound method, and so on. As a part of non-linear programming, you use KKT condition and the other considerations to solve the problem. If you look at the constraints, then subject to a set of constraints that the decision variable must satisfy, and this constraint can be categorized as equality constraint, Gix equal to 0, where I can take any value 1, 2, up to m. Inequality constraint, Hjx is less than or equal to 0, where j can take value 1, 2 up to p. And variable bounds, it means suppose my variable is space constraint, my variable is machine hours, my variable is number of workers, then it will have upper bound and lower bound. So your Lk is the lower bound of the variable xk and uk is the upper bound of your variable xk. So Gix are the equality constraint, Hjx are the inequality constraint, Lk and Uk are lower bound and upper bound respectively. If we continue with the generic formulation to have a better idea on the mathematical formulation of optimization problem, then the complete formulation is minimize or maximize fx. It could be cost function or profit function, subject to Gix equal to 0, Hjx is less than or equal to 0, inequality constraint, and you have the variable xk, which has a lower bound Lk and upper bound Uk. So typically the key aspects are decision variables that control or adjust to find the optimal solution, which can be controlled or adjusted. Number 2, objective function, fx, represents the quantity we want to optimize, minimize, or maximize. Number 3, constraints, gx, hx. Typically, it poses the limitations or restrictions that the decision variable must respect and satisfy. Number 4, variable bounds. So you have upper bound and lower bound for each decision variables. Broadly, if we look at then the types of optimization problems, linear programming, fx, gx, and hx are linear functions. Your objective function and constraints all are linear in nature. Non-linear programming, at least one of either objective function, that is fx or gx or hx, which are your constraints, are one of them is non-linear function. Integer programming, some of or all decision variables are required to be integer. So for example, you want to optimize the number of aircrafts to be deployed for a particular function or number of aircrafts to be manufactured for the given resources. You cannot manufacture, let us say, 1.7 aircraft, and here you must have the integer. Similarly, you want to have locate the warehouses at different sites. You cannot say I will locate 2.8 warehouses. Either it can be 2 or it can be 3. So here there are many conditions. For example, how many products I should produce. I cannot say I will produce 273.4 products. You can say the optimal value is either 273 or 274. So many situations, absolutely, I cannot have non-integer values for the practical purpose, and I must create the bound for the integral integer solution, and some of the or all of the variables are required to be integer. Number 4, mixed integer programming. So here, yes, you have the flexibility. Some decision variables are integer, others are continuous. It's not like the previous one, which is the pure integer programming problem. All the variables must take integer value. Here, you can relax some of the variables to take non-integer value, and the other variables are fixed to integer. Convex optimization, here your fx is a convex function and the feasible region defined by the constraint is the convex set. So that falls within the category of nonlinear optimization. There is one very important concept when we talk about typically the heuristics and evolutionary algorithm, and the concept is Pareto optimality in optimization. So what does it mean? Pareto optimality is the state at which resources in a given system are optimized in a way that one dimension cannot improve without a second worsening. It means there is a trade-off. For example, you want to increase the number of features to be provided in a car. So let us say number of features is the x-axis and the cost is the y-axis. Certainly, when you increase the number of features, your cost will go up. So your objective of minimizing the cost will be compromised. On the other hand, maximizing the performance or the features of the car is on the improvement side. So there is a trade-off. So you just see on the left side, you have a function f1x which you want to minimize. So as I move from right to left, I have the improvement. Because I want to minimize my function f1x, which may be the cost. Similarly, you look at the y-axis, I have f2x, it may be the risk. I want to minimize the risk. So as I try to minimize the cost or I try to minimize the risk, I am improving. Now, you see the figure where you can see the blue dots and the other dots are white dots. So all the blue dots are falling on a particular curve which depicts the non-dominated or Pareto optimal solution. And the other white dot which you see which are outside of this Pareto frontier, the graph, they are called dominated solutions. What is the difference? When you look at the blue dots which are on the Pareto optimality frontier, these dots, each one provides an optimal solution, meaning to say you are not compromising because you are improving on one function, and because of that the value of the other function is getting affected. Any one you choose on this particular optimal frontier, the blue dot, it gives you the best combination of f1x and f2x, and that is where it is called the Pareto optimal frontier. The solutions, all solutions are of non-dominated or Pareto optimal nature. So they are not dominated by others. But if you look at the white dots, yes, they are deviating from the Pareto optimal frontier. And if you are trying to improve, minimize the f1x, other hand, you are compromising with the f2x. This means minimizing the f2x. So when you are using the evolutionary algorithm and you are trying to deal with the conflicting criteria or trying to optimize two objective functions simultaneously, you want to figure out the Pareto optimal frontier and the solutions which are equally attractive. If I look at the first dot on the left side, it is equally attractive as the second dot is or third blue dot is, because they offer the perfect trade-off between f1x and f2x. Now let us look at the example, because this is a very important concept when you think about optimizing using evolutionary algorithm. Example of Pareto optimality. So let's say there is a scenario. A logistic company aims to optimize its delivery network, balancing two conflicting objectives. Number one, minimizing delivery time. So obviously you want to reduce the time it takes to deliver the package. And on the other hand, number two, minimizing operational cost. So reducing fuel consumption, maintenance cost, and labor cost, they falls within the part of operational cost. So I want to minimize the delivery time and I want to minimize the operational cost. F1x and F2x. What is the representation? We can represent the situation with a graph just like I have shown. Just visualize. X-axis represents the total delivery time and Y-axis represents the total operational cost. Both are expected to be minimized. Each point on the graph represents a possible delivery network configuration, different routes, fleet sizes, warehouse locations, and the feasible region is the set of all possible network configurations. Let us look at Pareto optimality in this context. A network configuration, typically your logistics network, is a Pareto optimal if there is no other configuration that can simultaneously reduce both delivery time and operational cost. So basically, you are looking for those non-dominated Pareto optimal solutions or the Pareto frontier, and that sets the premise for your Pareto optimality. If we continue with the example, then imagine the feasible region forms a curve and it indicates the trade-off between time and cost, and there are total 5 possibilities exist. Point A, non-Pareto optimal, high delivery time, high operational cost, and there are clearly better solutions available. Second, point B, that is the Pareto optimal, relatively low delivery time and relatively high operational cost. This might represent a network with more vehicles and faster route, but it sets the perfect trade-off between two objective functions, F1 and X2, delivery time and operational cost, and this gives you the optimal solution for the given condition. Point C, again, could be the Pareto optimal, relatively high delivery time. You are compromising bit on the delivery time, but you are gaining on the cost part, so relatively low operational cost, and this might represent the network with fewer vehicles and slower or more fuel efficient routes. Point D can also be the Pareto optimal. All point B, C, and D are non-dominated solutions following on the Pareto optimal, like your blue points, a balanced solution with moderate delivery time and moderate cost. Point T could be the non-Pareto optimal, not falling on the Pareto optimal frontier, outside it, and a solution with higher cost and moderate delivery time. It is dominated by point T. So the broader explanation is like this. Point B, C, and D are Pareto optimal. Moving from these points in any direction to improve objective will necessarily worsen the other. For example, to reduce the delivery time from point C, the company would have to increase its operational cost by adding more vehicles or using faster routes, and it may not be beneficial. Similarly, point A and D, which are non-Pareto optimal, because there are other feasible solutions which are better in both objectives. And the curve connecting points B, D, and C is called Pareto frontier. So here your point B, C, and D are basically blue dots, as you have seen in the previous graph. So there are many practical implications of this example, which is trying to minimize the delivery time and minimize the operational cost. First, logistics company can use Pareto optimality to identify a set of efficient network configurations. Number two, decision makers can then choose a configuration from the Pareto font based on their specific priorities and constraints. Number three, for instance, if the company prioritizes speed, it might choose point B. If it prioritizes cost saving, it might choose point C. You have a lot of options and combinations available depending upon the real life constraints. If they want to balance, number four, they will choose point D. Marginal compromise on F1X, maybe your delivery time, and marginal compromise on the operating cost, I can still have the optimal solution. So this approach helps the company make informed decisions by visualizing the trade-off between competing objectives. It also helps to avoid solutions that are clearly inefficient, like point A and point E. So let us take a deep dive into the core question: when a researcher should use optimization research approach. There are certain prerequisites and conditions. Number one, do you have a well-defined objective, a very clear goal of maximizing profit, revenue, market share, or minimizing cost, risk, waste, and so on? Can objective function be expressed mathematically? That is the prima facie of optimization problem. And measurable outcomes, is it quantifiable, allowing for comparison of different solutions and determination of the best one? Number two, decision variables. Do you have controllable factors? And these factors or variables that the researcher can manipulate or adjust to influence the objective function if some variable like maybe political disturbance or maybe the international trade issues which are absolutely not in your own control, then you cannot formulate or undertake the optimization based investigation research. Range of options, there is a range of possible values or choice for these variables. That is also an important consideration. You cannot have minus infinity to infinity, and within this lower bound and upper bound, you want to optimize your problem. The third is constraint. That is the limitations or restrictions. So are we in a position to define our constraint precisely and clearly? And do we have the limitations or restrictions that must be satisfied? So my ability to define the constraint precisely, like resource limitations, budget, time, manpower, physical constraint, capacity size, technical constraint, engineering limitations, regulatory constraints, environmental regulations. Can I define this into the mathematical terms with a very precise definition? If not, I cannot use the optimization approach. Number 4, need for the best solution. This is very interesting. Seeking optimality. Researcher aims to find the absolute best or most optimal solution, not just a good or acceptable one. And significant impact. Whatever optimal solution I am finding, it will have a significant impact on the outcome or decision being made. Many situations, suboptimal solution or the practical or realistic solution is more feasible and acceptable rather than the optimal one. So here it is the context, whether your context really demands seeking optimality or not, and will it have the impact on the outcome or the decision being made. So with these 4 conditions, which defines the prerequisite when a researcher should look for the optimization approach, let us look at the specific situation where optimization approach particularly is most relevant. One is the resource allocation, how to allocate limited resources. Budget, you have number of departments or functions, on what basis you will allocate the budget. Even you want to have the advertisement campaign and there are different ways of going for advertisement. How much budget you will allocate to the newspaper, to the TV, to the Netflix, social media, and so on. Second, scheduling and planning. Creating optimal schedules for production, transportation projects to minimize time, cost, maximize efficiency is a perfect fit for optimization approach. Design and engineering. Optimizing the design of products, structures, or systems to meet specific performance criteria while minimizing cost or maximizing efficiency. Number 4, logistics and supply chain management. You want to optimize the transport routes, warehouse locations, inventory levels, supply chain operations to minimize cost and maximize service levels. And number 5, finance and investment. You are interested to optimize your portfolio, mutual fund portfolio, or maybe maximize the returns while managing the risk. All this sets the perfect pitch for adapting the optimization approach and deriving the optimal or near optimal solution. Let us look at the example further of optimization. Let us say a researcher wants to determine the optimal production level for different products in a manufacturing plant to maximize profit, and they have information on production cost, selling prices, demand forecast, and production capacity. In this case, optimization would be an appropriate approach because I have the clear objective function that is maximize profit, which is measurable and quantifiable, decision variables, production level for each product, controllable in nature, constraints, production capacity, demand forecast. I can define my restrictions, limitations well. Need for best or solution, yes. it will have the impact on decision making or the overall profitability, and finding the production level that yield the highest possible profit is crucial. So by using optimization technique, the researcher can find the production level that maximize the profit, and this example or case becomes a fit case for using the optimization approach. What are the different types of optimization approaches? So broadly, you can say that first is the mathematical programming. Linear programming, we have already discussed. Your objective function constraint should be linear in nature. Resource allocation, scheduling, transportation problem, it is widely used. Non-linear programming, either your objective function or one or more constraints are non-linear, and it is more complex than linear programming. So finding the global optimum can be challenging because you may have a multi-model function or you may end up with the local optima. Various methods exist for finding the solution of the nonlinear optimization problem. It could be gradient-based methods, direct search method. So optimizing the design of a chemical reactor to maximize yield where the relationship between input variable and yield is nonlinear. We can have integer programming where either all the variables should be integer or binary, 0, 1, or mixed integer programming we have seen. And the examples could be optimal number of airplanes to purchase for an airline. You cannot purchase 2.7 aircraft, where functional airplane are not, fractional airplane are not practical or possible. Number 2, quadratic programming. It is a special case of nonlinear programming where the objective function is quadratic in nature, and obviously it is nonlinear function and the constraints are linear. So quadratic programming, I have objective function which is quadratic, nonlinear in nature, and my constraints are linear. It can be solved using some specialized algorithm. So portfolio optimization in finance, where the objective function is to minimize the risk, which is quadratic in nature, subject to linear constraints on investment amount, is a perfect example of quadratic programming. The another mathematical programming optimization approach is dynamic programming. It is used for problems that can be divided into smaller, overlapping subprograms or subproblems, and by solving each subproblem once and storing the results, dynamic program avoids redundant computation useful for sequential decision-making problems. For example, finding the shortest path in a graph where a problem can be broken down into finding the shortest path to intermediate node is a perfect fit case for dynamic programming. The second broader category is calculus-based methods. You have gradient descent. It's an iterative method that moves towards the minimum of a function by taking incremental steps proportional to the negative of the gradient, and it is used extensively in machine learning for training models. Example could be finding the optimal weights in a neural network. So your neural network basically involves the neurons which needs to be charged, weightage is to be assigned, and you need to minimize the errors in this process because it has a direct impact on the prediction accuracy, and gradient-based approach for defining the weightages of the in the neural network is highly useful. Newton's method, it's a second order method that uses both gradient and the Hessian matrix of second derivatives to find the minimum. So convergence is much faster than gradient descent, but requires more computation for iteration. For example, optimization problems in control systems and structural analysis is a fit example for the Newton's method. The third domain is heuristics and meta-heuristics. So heuristics you can develop considering the scope and complexity of the problem. And typically, heuristic is a rule guideline that provide good but not necessarily optimal solution in a reasonable time. For example, very simple heuristics is first come, first served. The first customer will be served first is a very simple form of one of the heuristics. Often used for complex problems where finding the exact optimum is computationally infeasible. So, example could be constructing a feasible solution to traveling salesman problem by using the nearest neighbor approach is a good case for heuristic based optimization. The other category within this is meta-heuristics, evolutionary algorithms, and typically it's a high-level strategy that guide the search process of heuristics. They aim to escape local optima and explore the solution space more effectively. So genetic algorithm, one of the example, it is inspired by natural selection. GA uses a population of solutions that evolve over generations through selection, crossover, and mutation, and optimizing the layout of components or a circuit board to minimize your wiring length is one of the classic example for the use of genetic algorithm. Similarly, there are many evolutionary algorithms. I'm just citing a couple of them. Other most widely used is simulated annealing. It is inspired by the annealing process in the metallurgy. So annealing process basically is the stress relieving process and the kind of mathematical expression used in the simulated annealing process about the temperature setting and entropy. It is used to model the simulated annealing based evolutionary algorithm approach. So SA gradually decreases the probability of accepting worse solution to escape the local optimum. So one thread is common. I want to escape the local optima even though I cannot derive the optimal solution, let it be near optimal, but I don't want to end up with the local optima. So example could be optimizing the design of a communication network to minimize delays is a fit case for simulated annealing. Taboo search, it keeps a list of recently visited solutions in the taboo list to avoid revisiting them. Because already you have explored and investigated those solutions, there is no point in revisiting them when you are trying to search a finite space with hundreds of solutions. And then it explores the new areas of the solution space. So typically, scheduling problem, which is combinatorial, NP-hard problem with complex constraint can be addressed using taboo search. Swarm intelligence, it is inspired by the collective behavior of social insects or animals such as colonies, how your ant colony, they move, what is the trajectory they follow. Bird flocks, there is always a pattern and they try to optimize their travel, and this pattern has some optimization logic included. So examples include ant colony optimization, particle swarm optimization, and typically your routing problems in the vehicle routing typically or in the communication network, they can very well be solved using swarm intelligence or swarm particle optimization techniques. The other techniques could be constraint satisfaction, focuses on finding solution that satisfies a set of constraints without necessarily optimizing an objective function. Scheduling problem falls into this category. Stochastic optimization deals with the problem which has some of the parameters are random or uncertain, and techniques include stochastic programming, robust optimization, typically optimizing inventory levels when demand is uncertain. So as a caution, I would like to mention the choice of optimization technique depends on the specific characteristics of the problem, such as the linearity of the objective function and the constraints and the type of decision variables presence of uncertainty and computational resources available. Broadly, you can see what we discussed, that optimization approaches are divided into deterministic method and stochastic method. Within deterministic method, we have branch and X, typically it is branch and bound. There are various variants, branch and cut, branch and price, constraint programming, dynamic programming, which divides the problem into sub-problem we have seen, optimized path approach. If you look at the stochastic method, then you have heuristic algorithms and stochastic algorithms. Within heuristic algorithms, you have meta-heuristics. Problem-based heuristics means you develop the heuristic considering the nature of the problem, and it is a uniquely designed heuristic for the given problem. Or you can use the meta-heuristics. Meta-heuristics, you have single solution-based meta-heuristics, or you have population-based meta-heuristics. So typically, let us see a couple of applications of optimization approach for, let us say the first one is vehicle routing problem. Some of the most promising problem in transportation and logistics domain. How do you route the vehicles? Typically, you think about maybe the vehicle routing for collecting the milk and then depositing it to the dairy, or maybe you are routing the vehicle for optimizing your distribution or the delivery schedule and so on. So the problem is determining the most efficient routes for a fleet of vehicles to deliver the goods to multiple destinations while minimizing the cost, fuel and time, adhering to the constraints, delivery windows, vehicle capacity. For example, there is a food van and they have to, let us say, take the meal, lunch from the centralized kitchen, typically Akshay Patra case, and then they are distributing it to the different schools for the children. And it is very important because it is perishable and they have to respect the time window. They adopt an optimal route, and this can be done using the vehicle routing approach. So optimization approach is mathematical modeling. Typically, you can use integer programming. You can use heuristic algorithm like genetic algorithm and simulated annealing are widely used. And you can use meta-heuristics approach to find the near optimal practical solution. Impact is reducing transportation cost, improving delivery times, and enhancing customer satisfaction. So typically, the mathematical formulation of vehicle routing problem is like this. I have the variables xij, k, which is binary variable. One, if vehicle k level travels from location I to j, otherwise it is 0. And uik, auxiliary variable representing the load of vehicle k after visiting location I, because you may unload some of the material and then you have a space to accommodate and when you are moving to the next destination. Parameters are Cij, cost of traveling from location I to location j, Qi, demand at the location I, Qk is the capacity of vehicle k, V is the set of location, k is the set of variables. Your objective function is to minimize the travel cost, minimize sigma I belongs to V, sigma j belongs to V, sigma k belongs to V, Cij, Xij, k, and it is subject to the constraints like each location visited once. So sigma k belongs to k, sigma I belongs to V, Xij, k equal to 1 because exactly one time it visits the location. Each vehicle leaves the location, it enters. So epsilon I belong to V, Xij, k equal to epsilon or sigma j belongs to V, Xjik. It's an equilibrium constraint. Vehicle capacity constraint, you have uik minus ujk plus qk xijk should be less than or equal to qk minus qj. And likewise, you have elimination of the subtour and binary constraint because your xijk should take either 0 or 1 value. The other optimization problem example is supply chain network design. The problem is to optimize the location and capacity of warehouses. distribution centers, and manufacturing plants to minimize overall supply chain cost while meeting the customer demand. The optimization approach, which is widely used, is linear programming, mixed integer programming, and network flow optimization to analyze various network configurations and identify the most effective design. Impact, obviously, reducing the inventory holding cost, transportation cost, lead time, leading to a more efficient and responsive supply chain. Typically, the mathematical formulation goes like this. I have the variable yj, binary variable, 1 if a facility is located at location j, or it is 0, otherwise xij is quantity shipped from facility I to customer j. I have the parameters fj, that is the fixed cost of opening a facility or warehouse at location j. Cij is the cost of shipping one unit from facility I to customer j. AI is the capacity of the facility I, dj is the demand of the customer j, I, capital I, is the set of potential facility location. You cannot just locate it anywhere, you must see the feasibility. And j is the set of customer location. You have specific markets to serve. So objective is to minimize the total cost, minimize sigma j belongs to I, fj yj plus sigma I belongs to I, sigma j belongs to j, cij, xij, that is the cost component. Constraints will include demand constraint. My sigma of xij should not exceed, it should meet the dj, that is the demand. Facility capacity xij, sigma of that should be less than or equal to ai yi. Non-negativity, my xij variable cannot be negative, should be greater than or equal to 0. And binary constraint yi, it is the location of the facility, either it is 1 or it is 0. Application of optimization approach also we can see for container loading problem. This is again a very distinguished and interesting problem. So the problem is maximizing the utilization of container space while considering the factors such as cargo weight, dimensions, and fragility. Optimization approach is 3D packaging algorithm. Heuristics methods, many times it is used to determine the optimal arrangement of goods within the containers. And impact reduces shipping cost by maximizing container utilization and minimizing the risk of cargo damage. So broadly, the mathematical formulation will go. This problem is often formulated using complex 3D packing algorithms and heuristics rather than single, concise mathematical formulation. The core concept would remain same, where your objective function is subject to, which is maximizing volume utilization, to constraints. My variables for this problem, container loading problem, is pi, position of item I in the container, 3D coordinates, OI is orientation of the item I, bij is the binary variable, 1 if item I is placed before item j, otherwise it is 0. You have the parameter li, wi, hi, dimensions of the item A, I because it is a 3D, and lwh, dimension of the container, again it is 3D. So you want to maximize the total volume of items packed. So maximize sigma I, li, wi, hi, subject to the constraint, non-overlapping constraints, very complex to express mathematically, container boundary constraints, stability constraints, and weight distribution constraints. Let us look at another very interesting problem in optimization, that is traffic flow optimization. My problem is to minimize the traffic congestion in the city. Many of the city, Delhi, Bangalore, Chennai, they are really flooded with the traffic, and this problem has significant importance in solving the traffic congestion. And I want to improve the travel times in the urban areas. Optimization approach, mathematical modeling of traffic flow, simulation techniques can be adopted, control algorithms are used to optimize traffic signaling and routing strategies, and impact would be reduced travel times, fuel consumption, emission, improving over traffic efficiency. So my mathematical formulation would for traffic flow problem would go like this. Variables, I have xij, flow on link ij in the network. Ti is the signal timing at intersection I. Parameters Cij, capacity of link ij. Dj is the demand at node j. Objective is to minimize total travel time or congestion. Minimize sigma ij f xij, where f is a function representing travel time or the congestion. The constraints would be flow conservation, sigma j xij minus sigma k xki should be equal to di, which is demand at node I. Link capacity constraint xij, that is the flow on link ij, should be less than or equal to cij, capacity of the link. For example, I am considering a particular road or bridge, highway, and it has a capacity to accommodate 100 vehicles in a given length or per unit time, then my xij should be less than or equal to cij. The another application to eliminate the concept of optimization is for very, very recent and most demanding area, multimodal transportation. Multimodal transportation is very much part of public, urban, city planning, as well as it is for the freight, passenger as well as for the freight, how you can change the mode of transport, reach to your destination within time at a lesser cost with less hassle. Similarly, it applies to the freight. So problem is finding the best combination of transportation modes, trucks, rail, ship, to move goods from origin to destination, considering cost, time, and reliability. So optimization approach is network optimization models and multi-objective optimization techniques, which are widely used to evaluate different multimodal transportation options and select the most efficient one. Obviously, impact is reduced transportation cost, improved delivery flexibility, and enhanced supply chain flexibility. The mathematical population can go like this for multimodal transportation problem. Variables xijk, quantity of goods moved from mode I to node j using the mode k, whether you are using rail, k is the rail, or road, or ship, or air. Yik is the binary variable. 1 if mode k is used on link I, 0 otherwise. I have the parameters Cij, k, cost of moving one unit from node I to node j using mode k. Suppose I am transporting my freight by truck, road, then what is the cost? And if same I am transporting by rail, what is the cost? Tij, k, similarly, what is the time of moving one unit from mode I to node j using mode k? If I ship it by rail, how much time will it take? If I ship it by air, if I ship it by road. So we need to see the trade-off. Trade-off between travel time vis-a-vis the cost involved, and AIK is the capacity of mode k on Lincoln. My objective function is minimize the total cost or time, minimize sigma ijk, Cijk, which is the cost associated with a specific mode k, or minimize sigma ijk, where Tijk and Xijk deals with the time constraint. My constraints could be flow conservation, mode capacity constraints, demand satisfaction, time window constraint, and the binary constraints. So I hope this formulations and the mathematical approach, as well as with the explanation about the importance of the problem in its impact, would have helped you to understand the importance of the optimization approach in solving many, many real life complex problems. So to conclude this session has provided you the broader understanding of optimization, the different kind of optimization approaches involved, the application areas, and then typically for the transportation and logistics sector, how do you define the problem? And once you have defined the problem, how do you convert it into the mathematical formulation? And also for a given class of problem, what is the best way of solving that problem, whether it is the linear programming approach or integer programming approach, or it is the nonlinear optimization, or it is the use of evolutionary algorithm or meta heuristics, or you develop your own heuristics, which is contextual for a problem. All these approaches we discussed to bring clarity on the use of optimization approach. So about my university, Gati Shakti Vishwavidyalaya is India's first and only university in transportation and logistics sector, has a unique role to play in terms of creating highly skilled manpower for all the modes of transport, rail, road, aviation, water, ports, and shipping. GSV extends programs at all levels, undergraduate, postgraduate, PhD, and executive training to enable nation's aspiration to reduce its logistics cost from present 14% to 8 to 9%. Transportation sector is a growth engine for India, which contributes roughly 6.3% of GDP of India. The university offers demand-driven curriculum with a focus on all three dimensions: technology, that is infrastructure; management, that is services; and policy, that is regulation, covering all the modes of transport: rail, road, water, aviation, ports, and shipping, to strengthen the ecosystem of multimodal transportation and logistics in the country. In line with the vision, innovation-led industry-driven university, Gati Shakti Vishwavidyalaya has collaborated with the various leading industries such as Airbus, Nippon Koi, Nokia, Siemens, Jacobs, Plaza India, Railtel, others, to significantly strengthen the ecosystem of transportation and logistics sector in India and across the globe. Thank you very much for your interest in learning the various dimensions of faculty and student development. We will keep exploring more issues through this platform for the benefit of faculty and students, most critical entity in the higher education in India. Thank you very much.